We saw that rearrangement in addition reactions is possible, but sometimes we don't want that. We want to get a specific product. Depending on what you want to add to the molecule, you can actually choose a set of reagents to achieve the reaction without rearrangement. In this case, we're going to do a addition reaction, or specifically a hydration reaction that doesn't involve rearrangement, and it's going to be called oxymercuration demercuration. So when we added the H2O, the water across the double bond in the previous video, we had water and we had some acids. So just, acid catalyzed hydration, that's what we used. But in this case, we also add mercuric acetate. So I'll draw that a little bit below, but it's just mercury with two acetate groups attached to it. This reaction actually differs from acid catalyzed hydration right from the beginning. Something that I've added is that the mercuric acetate dissociates to form a mercuric cation, which I've drawn here. What's going to happen is instead of the double bond attacking and distracting a proton, it's actually going to attack this mercury atom. Just as we'd expect in terms of where the mercury atom will add, as we saw with where the hydrogen atom add, it's going to add at the least substituted position. So I'll have the Hg here with the acetate still attached. And we have the carbocation right here. Now here's the interesting thing, because the mercury atom has a lone pair, and this lone pair is actually going to interact a little bit with the positive charge. And we kind of get this resonance structure that has carbocation character and also a three-membered ring. So what this looks like is, to illustrate how the electrons interacting with the positive charge, is we have the mercury becomes this kind of three-membered ring right here, and then it takes the positive charge. What this does is it actually eliminates the full carbocation character, which prevents rearrangement, and here's where that comes in handy. So once we've done that, we can have our nucleophile, which we should expect to be water, as we see with the acid catalyzed hydration, to come in and attack at the more substituted position. This is still Markovnikov addition. So this comes in and attacks right here, and we could view it as the electrons, in this case, moving back onto the mercury atom. And we get this. Now keep in mind, the mercury acid is still attached, but we have added the water. So that would be here. And I'll go ahead and skip the proton transfer just for the sake of time. Now the last step, in order to get the product that we want, all we have to add is essentially do the demercuration part. And we do that with sodium borohydride. You don't need to know a mechanism for that. But looking at the whole reaction, we see it works in very similar ways to what we've viewed in the previous video. We have a double bond attacking and abstracting something, and we're creating a positive charge. But in this case, the reagent that we added, the mercuric acetate, prevented rearrangement by removing the full carbocation character. Thus, we get this product over here plus the enantiomer. Why the enantiomer? Well, since we have this bridge right here, we see that the nucleophilic attack happens as an SN2 mechanism from the back. And we actually get a bit of an anti-addition. Typically, that's not going to be too big of an issue. But the important thing to realize is that we can add the OH on either side of the molecule. So we get both the S and the R stereochemistry here, since there is a chiral center. The oxymercuration demercuration that we viewed in the previous slide allowed us to achieve a hydration without getting rearrangement in the product, but we still got a Markovnikov addition, adding to the more substituted position. What if we want an anti-Markovnikov position, as we have shown here? Well, it's possible, and it's called hydroboration oxidation. So the first part that actually achieves this is we're going to add borane. And that's going to explain most of what's happening with the anti-Markovnikov addition. The first part of the mechanism goes as such. We're going to have the double bond act as a nucleophile, and then we're going to have the electrons in one of the bonds between hydrogen and the boron to fill the other spot. As you can see, the result of this is that we've added the borane to the last substituted position. And I'll go ahead and show the hydrogen as well. But the question is why? Well, one thing to notice is that borane is actually flat in its geometry, and so is the double bond. So in order to get the orbital overlap, in order to get this reaction right here to happen, we actually have quite a bit of steric hindrance than what we'd expect for sp2 hybridized atoms. And the idea is we want to put a larger part of the molecule away from the rest of the molecule that we're adding to. Another thing is that in the transition state, we're putting more of, in this one, we're putting more of a partial positive on this carbon as opposed to this one. And we prefer to put it on the secondary carbon. So there's both steric and electronic considerations here. The next part of the reaction, or the next step, is that we add sodium hydroxide and hydrogen peroxide, so H2O2. Now, the mechanism for this is pretty complicated, and I won't go into very much detail, but the idea to realize is that once we add that, which would be going to add to this step, we go directly to our product. So that takes care of, in a way, if you look at it, we're replacing this borane with the OH. However, there is one more consideration to think of here, and it's how the borane actually adds. Considering that it's flat over here, and we're adding two groups at the same time. We're adding this hydrogen, and we're adding the borane, which you see right here. Considering the way they have to interact and get the overlap of the orbitals, they add on the same side of the double bond. Now here, when we look at our product, we didn't see any obvious stereochemistry with this syn addition, and that's what we're talking about. But you'll want to keep in mind, we'll see other examples in some later videos in which we do get some stereochemistry to consider when we have a syn addition with hydroboration oxidation. The key part to remember is that we have the hydrogen and the borane adding on the same side of the molecule at the same time.